Good afternoon. Welcome to this next session of the Decisions, Games and Evolution meeting. It is my pleasure to introduce Professor Vivek Borkar, who is from IIT Bombay. Professor Borkar did his PhD from the University of California, Berkeley, and after that he moved back to India, where he started his first faculty position at the Center for Applicable Mathematics, which is a TIFR center in Bangalore. And
I thank the organizers for the invitation and Supratim for a generous introduction. So I have sort of put decision, the word decision in boldface for a good reason. That's where I belong more or less. I've taken examples from games and evolution, etc. But that's not my expertise. And another comment is that this is not the entirety of my slides. Supratim wanted me to talk about Markov decision process and reinforcement learning. So I'll try to build up to that with this set of slides because that's a lot more technical. Okay, so this is the summary or overview of this particular set of slides. Anyway, I'll see what all this is as I go along. And there's some color code. The main I myself cannot see the color well. Okay. The main content is in deep blue, and highlighted material is in red. And occasionally there's some advanced material which I felt obliged to include for sake of completeness, because otherwise somehow, it's part of the whole sort of subject, so I can't just leave it out. But if you find it difficult, just ignore it. It's kind of standalone, it won't affect anything else. There's not too much of it, only a couple of places. Okay, so first thing I want to peddle is this idea of algorithms and dynamics. So I took this definition of algorithm from Wikipedia. So of course I added the parenthetic material there. So an algorithm is a finite sequence of mathematically rigorous instructions typically used to solve a class of specific problems or to perform a computation. So this I claim is the classical deductive view of algorithms. You start with something, some axioms and assumptions and rules of how to combine them, and then keep combining them repeatedly till you come to some conclusion. And of course, there are standard large amount of theory built around how to evaluate them. For discrete algorithms or computer science algorithms, it's complexity theory, which sort of quantifies how many computations, elementary computations you need as a function of the problem parameters. And in numerical analysis, it will be convergence rate, and say it's k times alpha raised to n. Say, then what the exponent, what the alpha is, and what the k is, etc. Now the thing is that this is not always the case, and that's I want to talk about the other side of algorithms, which is what you see more in statistics or AI or machine learning. And this is more of inductive reasoning. You are getting random samples, noisy samples, one after the other, and trying to infer something from that, using some either rigorous principles or occasionally with just heuristics. And this I want to distinguish from randomized algorithms, which are classical algorithms where you use probability, you add noise with some purpose. That's different from what I'm looking at, where what you get is noisy already. You don't choose the noise. So these are, as I said, the algorithms in statistical computations or machine learning. And sort of they're characterized by these things. One is, as I already said, they're noisy observations, and they're incremental and iterative. So what I mean is that you just keep repeating something with a small increment at each time. Okay. And the reason for that you will see soon. And anyway, one consequence is that typically per iterate computation is low. So if you may run the convergence till eternity, or at least till near convergence. So if you just sum up the total computation I did, it could be a lot, but at each time, each step you do, typically do very little computation and require very little memory. You kind of amortize the total computation budget over time. So it will typically look like this. Any questions so far? Anyway, you are, I know that the audience has mixed background, so there's a risk that I may go fast at times. So stop me if there's any question. I'm used to teaching engineers and applied mathematics people, so I may take a few things for granted once in a while. Okay, so this is the typical algorithm. And so my current iteration is xn, I go to xn plus 1 as xn plus some positive step size an, which I choose, and this is my measurement. This entire bracket is what you get. You don't get hxn and mn plus 1 separately. So h is some function, and mn plus 1 is a noise sequence satisfying this condition. So conditional expectation of mn plus 1 given everything you know till n is a 0, basically. So past till n just means all random variables which were realized till time n. Conditioned on that, the mn plus 1 is something you see at time n plus 1. Conditioned on everything till n, the conditional expectation should be 0. And I have said that it's uncorrelated with past, and that's because the statement implies the following. Zero. So take any random variable which was already there at time n, it's uncorrelated. Okay. So it's uncorrelated noise, and there's another misconception that it's additive uncorrelated noise for sure, which may look restrictive because of the additive nature, but it's not so, and that's what I explain here. So typically your algorithm will look something like this. So f of, instead of that hxn plus mn plus 1, you will have f of xn comma xi n plus 1, where xi n plus are typically IID. I mean, I'm taking a simple case. The independence is more important. And this is not additive noise, but then what I can do is I can just add and subtract one step conditional expectation of f xn xi n plus 1 given xn equal to small x. So I define hx this way, if I freeze x and just average out over this independent noise, and then add and subtract hxn to get mn plus 1 defined this way. And hxn is a one-step conditional expectation of this. So conditional expectation of mn plus 1 given everything up to n is 0. So I can always reduce an algorithm like this to this form. This is what one typically does. It's not, a typical reinforcement learning algorithm may look this way. But then you just do this trick and it reduces to something more familiar. Yeah. No, that's a continuous time process. Later on, I will talk of a class of algorithms more general than this. This won't, okay, see, I'm going to analyze this by taking a continuous time limit. That gives a ordinary differential equation, not stochastic differential equation. So for stochastic differential equation, you have to add noise on the, this I see a typo just here. It should have been an. The noise has to be plus square root an times something. No, m is a noise, but it's multiplied by an. So to get a stochastic differential equation limit, I'm going to let n go to 0 at a certain rate. N goes down too fast. Okay, so this is called Robbins-Monroe algorithm. And of course, Herbert Robbins and his student Sutton Monroe, they looked at a specific case, but basically the same idea can be pushed. And the clever thing was they imposed these two conditions. People also look at constant step size, but let me first talk about this. So this gives typically probability 1 results, convergence to some desired limit with probability 1 or to some limit set with probability 1, etc. Constant step size won't give you that. It will typically give you high probability concentration. the desired limit. But it has advantages that it's simpler to implement, and usually in many applications, the environment slowly varies. So if you use, I'll later on interpret n as a time step, when you take the continuous time limit, then n going to 0 means the algorithm is becoming slower and slower. So once it becomes slower than the environment, it won't track anything. So for tracking applications in, for example, signal processing, this is preferred. Just I will stick to the decreasing step size, but just something worth knowing. So let me return to here's Robbins. So he had was an interesting person. So he did his PhD in pure mathematics with Hassler Whitney at Harvard, and then joined Navy during World War II. And once he overheard some Navy people talking about optimal bombing patterns. I mean, there are various accounts of it. According to one, which I don't know whether that's reliable, it was for the Normandy landing. Anyway, this guy did the calculations for them, and then got more and more involved and turned to statistics. He is also the Robbins of the famous book, What is Mathematics by Courant and Robbins. So all the mathematicians who got inspired by that book keep wondering what happened to Robbins. The answer is that he became a statistician. And he did, in addition to Robbins Monroe thing, he did many other things. There's something called empirical base. And this famous Lie Robbins paper on multi-arm bandits. So that's currently a very hot area, and so on. And okay, the one more important thing, he had many PhD students, among them 2 Indians who became famous statisticians in their own right. One is Raghuraj Bahadur and Gopinath Kalyanpur, who was briefly director of IISc. Okay, so let me, with a brief interlude, let me return to this. So I'm going to follow one particular viewpoint. I mean, this is not the only way of analyzing this. In fact, the early works did not do this. This came in 70s from the Russian school, later on picked up first by Lennart Ljung in Sweden, and then several others, which is to view this as a noisy discretization of this differential equation. So noisy because there's this noise, and it's a discretization with I treat n as a time step. So if you just consider xn plus 1 is xn plus a times hxn, that's what's known as Euler's scheme in numerical analysis. That's how one often implements the differential equations on computer. But this is slowly decreasing step size, and there's noise as well. So I'm assuming it is well posed. This word I may use often, and also I sort of assume it even if I don't say it. I'll assume every time I have an ODE, it's well posed. Namely, it has a unique solution for each x, and that solution depends continuously on x. So solution, of course, is a continuous trajectory. So I'll look at the map from x to the space of continuous functions, and starting at x, and the map from x to the continuous function which started at x is continuous. And the claim is that xn under reasonable conditions will track the behavior of the ODE. So if the ODE converges, the algorithm converges with probability 1. And this is, I always sort of promote this as a selling point. Any convergent ODE is a template for an algorithm. And you'll see some examples. In fact, I'm going to focus initially largely on 3 paradigms, 3 ODEs which correspond to several algorithms. So now, given that interpretation, I can interpret the conditions which Robbins and Monroe pulled out of the air. I mean, they weren't thinking of it as an ODE. But this thing, what this ensures is that the entire time axis is covered because n is by time step. So I want to track the asymptotic behavior of the differential equation. So if sum of n was finite, I would simulate the differential equation of finite time, and that won't capture the asymptotic behavior. Now, this condition is important. This in particular implies n goes to 0. So discretization errors go to 0. That's the simpler part. For that, n going to 0 is enough. This is a stronger condition. But this also ensure that the errors due to noise go to 0. And that's because this is the cumulative noise from 0 to n. One can show that this converges with probability 1 as n goes to infinity under reasonable conditions. I have not For example, if this is second movement is bounded, that would be enough. Then, so if this converges, then what it says is that the time, same sum from n to infinity. Since the convergent series, this makes sense. The sum from capital N to infinity is the tail of a convergent series, so that also goes to 0. So noise added from time n onwards goes to 0, and therefore the error due to noise also goes to 0. So the actual proof goes as follows. So you defined some discrete time sequence starting with 0. So T0 is 0 and Tn is this sum. And then let x bar t be xn for t equal to tn. So basically a plot xn versus tn and interpolate linearly. So that gives me a piecewise linear continuous function. And then at fix some time t and consider s greater than or equal to t. I start this differential equation trajectory at time s with exactly the same value as x bar t. Sorry, at time t with where it is matched with x bar t. And the claim is that this on a moving window, these two approach each other. And I have a picture. So I keep moving a window from S to fix some capital T, doesn't matter, S to S plus T, and keep moving it to the right. So from S I have gone to small t and then small t plus capital T. So this jagged curve is the interpolated piecewise linear trajectory. I have plotted xn versus t against tn. I interpolate linearly, call that x bar t. That's this piecewise linear curve, which goes more and more rough as you go. And then when I consider this interval of width t, I start here a differential equation trajectory with the same initial condition. And as I sort of shown here, they get closer and closer. And that's because these two errors are becoming asymptotically negligible. Okay, so I think I seem to have missed something. Yeah, okay. So this itself doesn't tell you where it goes, but suppose I can say something about the ODE, then one can infer the same for the algorithm. And I think this is out of place probably. Okay, maybe I missed a slide somewhere. So yeah, so the idea, I'll give a more precise statement later, but in algorithmic applications, often you have some Lyapunov function that decreases strictly along any non-constant trajectory of the ODE, ensuring convergence to an equilibrium. And because the two are approaching each other, so suppose it decreases over some interval by some amount delta, because the interpolated iterates are coming closer and closer to the ODE, they will decrease along those iterates also by delta by 2 or something. And you can reduce the delta as you move forward in time. So you get the same limiting behavior as the ODE. And more generally, if it's not convergent, you can say something using this what's called Lassalle's invariance principle. It will converge to the largest invariant set, which is to be defined later. You probably know it already anyway, but I need a formal definition. Largest invariant set contained in the set where the gradient of the Lyapunov function vanishes. Yeah, yeah. It depends on the problem. These are much more general result. The rate will depend on the specifics. Yeah. I mean, there are some genetic results also. So for these algorithms, there's a central limit theorem, law of iterated logarithms, all such things have been proved. More recently, concentration inequalities also. So you can say that typically for, anyway, I'll talk about strong law of large numbers later, then things will become clearer. Okay, so the set of A is said to be invariant for the differential equation. If you start a trajectory at some point x in A, it remains in A for both t positive and t negative. This is important. This is why I write the definition. It's not just for t positive. It's said to be positively invariant if you start at x and remain thereafter. But I also want it in the opposite direction. Okay. Now, this will, anyway, I'll read this. It's not worth remembering, but I'll show a picture. Invariant set is said to be internally chain transitive if for any xy in A and any epsilon positive, t positive. We can find some n greater than or equal to 2 and points xi such that for each I, there exists a trajectory of the ODE starting in the epsilon wall around xi and ending in epsilon wall around xi plus 1 after a duration greater than t. Anyway, this is a notion due to this man Conley. I will say more about him later. And in fact, if I took x and y in A, if y is x, that means you are looking for trajectory from x to itself and make this statement, it's said to be internally change recurrent. That's also an important notion in Conley's theory. So these are the pictures. So I have x and capital X, instead of y I have written capital X. And then this, okay, given these 2 points, okay, this ellipsoid is my invariant set. I say it's internally transitive if I've given any 2 points and any epsilon and capital T positive. I can find some n points somewhere and draw epsilon balls around all of them. Then I have some trajectory starting here, which after some time after capital T goes here, some trajectory starting here, which goes here, and so on. So modulo some small jumps, I can go from anywhere to anywhere. That's the idea. It need not be true that I can find a trajectory from here continuously going there. So the main theory, most general statement about these algorithms is that due to Michel Benheim is that Xn converges with probability 1 to an internally chain transitive invariant set of the ODE. And I mean, this may look a little too pedantic, but there's a reason I'm going through this, because since games is one of the, game dynamics is one of the interests here. I work mostly in single agent kind of optimization problems or single agent control problems, where you do, if you have a reasonable algorithm, you will converge. Maybe multiple equilibria, but still nothing worse. But once you have multi-agent scenarios, it goes for a toss. If at some point, people working in, and maybe they are already doing so, people in learning and dynamic learning in games will have to live with this kind of jugglery, I mean, internally chain transitive sets and so on. So suppose anyway, in our case, for algorithms, unless you have designed them badly, typically only such sets will be isolated equilibria. And if the noise is rich enough, then one good thing is that if under this rich enough, I'll explain, you go through, with probability 1, you will converge to one of the stable equilibria. And the other result is that every stable equilibrium or a attractor has a strictly positive probability of being a limit of Xn. So it avoids things like local maxima, saddle points, and so on. But you cannot guarantee it will go to a desired, sorry, let me backtrack. Suppose you consider just stochastic gradient descent, the most popular of these schemes. Then the equilibria are local minima, local maxima, and saddle points, and maybe some points of inflection, if any. So this tells you that it will go to a local minimum. That much is already guaranteed if the noise is rich enough. And the other thing is that every stable, this is the sort of negative thing, every stable equilibrium, or in this case local minimum, will have a strictly positive probability of being a limit. So this actually is a simple fact. It was proved in a paper by Kaniowski and Arthur, which does a lot more. But suppose you have some 2 local minima. Because of the noise, anyway, so suppose it's here. Because of the noise, it will tend to, because the gradient is this, it will tend to move here, but you cannot eliminate the probability that's because of some bad luck you got here. This is a positive probability. It could be small, but it's there. Once it's here, with high probability it will go here. So that's basically the proof of the last statement. Every stable equilibrium will have a positive probability. Now the previous statement needs a proof, and I have a picture here. So this is a typical, I probably say this elsewhere, but I shall assume that all equilibria are hyperbolic in the sense that the local, if you consider if you linearize H at that point, consider it Jacobian, then its eigenvalues are not on the imaginary axis. Okay. So they are either the left half plane or right half plane. And the reason is that this assumption makes it structurally stable, this picture, in the sense that if I perturb the dynamics a little bit, the curves will get distorted, but it will still look the same. And that's important because we are looking at a noise perturbed system in the first place. There is only a limit. So if it's not structurally stable, you are not going to get much out of it. So this is a hyperbolic equilibrium with one. So this is a stable manifold. So this corresponds to eigenvalues which are in the left half plane. So if you are on this, you will converge. This is the unstable manifold corresponding to eigenvalues in the right half plane. So if you are on this, it will move away. But what's most interesting is what if you are not on either of them? You go like this. So the point is that unless you are exactly on the stable manifold, you diverge. And if the noise is rich enough, you will be kicked out often enough that you will diverge. That's why all unstable equilibria are avoided. This, I don't know, those who have done one course in major theoretic probability, there's something called, there's a Borel-Cantelli lemma, which you must have seen. There's a conditional version of it that sort of ensures that if you are on this and under certain technical condition, you will be pushed away often enough that you just leave. Any questions? I'm going to special cases now. Okay, so this strong law of large numbers which I mentioned, this is a special case of this, which is, so in fact, you can turn the statement around and say that stochastic approximation, convergence of stochastic approximation algorithm is some kind of a strong law of large numbers for certain kind of dependent random variables. So if I have xi IID random variables and Sn is the partial sums, then Sn and mu is the mean. Then Sn by n goes to mu with probability 1, that's the strong law of large numbers. And you can write, suppose that let xn denoted by xn this ratio Sn by n, then xn plus 1 can be written as Sn plus xn plus 1 by this, and just by manipulating, I get it into a stochastic approximation. Okay. So xn is it's xn plus 1 by n plus 1. So my an is 1 by n plus 1, which satisfies sum of an is infinity, sum of an square is finite. Mu minus xn is mu minus x is my h, and this is actually IID zero mean sequence. So the corresponding ODE is x dot equal to mu minus xt, and simple linear ODE which converges to mu, so Sn by n goes to mu almost surely. This of course looks like a simpler proof of SLNN, but it's not so because the effort required to justify the ODE is much more. No, but this immediately takes us to the EARN models, which is another extensively studied area. So simplest case is you add, so suppose you have some empty EARN and you start adding one ball at a time, either red or blue, and let xn be the current fraction of red balls. Then 1 minus xn will be the fraction of blue balls. And suppose the probability that the next ball being red, so I add a ball red or blue depending on what the current composition is. So the next ball is red with probability p of xn. See, there's only one sort of unknown xn, because the other one, I don't have to write xn comma 1 minus xn, which is just a single scalar variable. So this p is some function from 0, 1 to 0, 1. And then same argument shows that xn plus 1 will satisfy this stochastic approximation, except that xi n plus 1 is now replaced by p of xn. So the ODE will be x dot equal to px minus x, and it will converge to some, so I assume, did I say that? I assume that p is continuous. Yeah. It will converge to some, in fact, for it to be well posed, they should assume more than continuous, but I'll, without loss of generality, every ODE I look at is well posed. So the claim is that xt will converge to some x star, which is a fixed point of p. And there will be at least one such point, because this is 0, 1 cross 0, 1. Draw the diagonal. So this is my p. Take any continuous function p going from left to right, it has to cross the diagonal once. There's at least one x star. So that p x star is x star. Okay. And you can say more. I mean, if from the differential equation theory, you know that this. So the equilibrium is px star equal to x star. That's the characterization. It can be stable or unstable, and if you recall, I mean, for example, in linear system, x dot equal to ax, say, is stable if the eigenvalues of A are in the negative half plane and unstable otherwise. So here I have to consider the linearization. That my equation is Px minus x. So the kind of Jacobian will be just a scalar function, which will be P prime x minus 1. Okay. So these are exactly these points. So here the slope is less than 1, is stable. Here the slope is bigger than 1, it's unstable. So actually even the discrete iterations, you will see that if I start here, it will get mapped here. Then the composite with that function again, it comes here, and so on, it will converge here. And same thing is true for the continuous dynamics. It will converge to one of the stable equilibria. Now, more generally, so this is something which I want to kind of advertise, so to say. So, more generally, consider Fi non-negative. Of course, they shouldn't be all zero at the same time because I'm dividing by this. So, consider if I write this differential equation, if I sum over I on the right hand side, I start with a probability, start in a probability simplex. The initial condition is a probability distribution, say. Then you see that it's invariant because if I sum over I get 0. So sum of xit will remain 1. So this is the ODE limit of this equation, which generalizes the R model, where this xi n, this indicator xi n equal to I. Yeah, actually, maybe I should write it down. In of dot 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 will be 1 if dot 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 is true. If not, so this I'm doing because the convention changes. So probabilists use I because chi stands for characteristic function in the Fourier transform. Mathematicians other than probabilists use chi. So just to disambiguate that, I'm defining it here. It's like electrical engineers using J for square root of -1 instead of I because I is the current for them. So I assume that the conditional probability that the next, this should have been +1. Yeah, I think, yeah, this is consistent with this. It should have been +1 here and +1 here. P of psi n +1 equal to I, yeah, it has to be n +1. And given everything up to n is pi xn. So then from this you get this differential equation. This is quite general. I mean, I'll give several examples of this. So if n is 1 by n + 1 is just you start at with 0, it reduces to Cesaro sum up to time n. Now this in probability there are this Kolmogorov forward and backward equations. So actually, if you consider 2 time points, suppose I have t bigger than s, I am at x at time s and y at time t. Okay, then probability of being at y at time t, given that you are at x at time s, will depend on 4 variables, x, s, y, t. If I freeze xs, I fix the initial data and consider the evolution in y. That's called the Kolmogorov forward equation, which generalizes Fokker-Planck equation. Kolmogorov did that for Markov process in general. If you fix yt or some terminal expected value of some function at time t, say, and write the equation in x and a, it's called the backward equation. So I'll need only the forward equation, which is for the continuous finite state continuous time Markov chain is just x dot t p transpose xt minus xt, where p is a stochastic matrix. Or you can write p x dot t equal to q transpose xt, where q is p transpose minus I. That's called a rate matrix. So given this is a linear case, so what the previous equation I wrote, you can think of this as a nonlinear Kolmogorov equation. And this I claim is a good template for RL for reinforcement learning, which adapts selection probabilities based on the observations. And I call it stateless RL because I am not imposing any dynamics for the, there's no dynamics imposed on the observed process. Just some samples coming here. So later on, if I get that far, when I do reinforcement learning for Markov decision process, it's different. It's a dynamic process in the background where you are trying to learn something. So this is actually some of the early work on this kind of thing was done by Robin Pimentel. It was on vertex reinforced random walk, where the probability of being in the next state being J is some increasing function of number of past visits to J. It doesn't have to be increasing, but in some of the applications that happens to be the case. He also studied age reinforced random walk, where I think it's the probability. Yeah, this could be erroneous. I think it's the probability of traversing an edge depends on the number of times you visited that edge. So when you are at Xn, you go to J depending on how the fraction of times you went to J in the past. So this is another observation about ODEs. If I have this ODEs, y dot t is hyt and z dot t is at times hzt. And suppose at is positive and total integral is 0 to infinity is infinite, then they have the same trajectories. Okay. So suppose at was, say, some constant a, suppose at is 2, then z dot t is 2, zt, it will follow the same trajectories twice as fast. If it is half, it will go half as slow, and so on. So this doesn't change the trajectories. So you just look at a trajectory with the same initial condition, they will go along the same trajectory with different speeds. So here, of course, depending on whether AT is bigger than 1 or less than 1, it can be modulated. But this AT, it's scalar. Scalar and positive is the only thing I need. It can be a function of ZT. So in this case, if I take this, okay, as my AT, then my non-uniform column is equivalent to this equation. And if Fi is UI, Xi UI, this is the replicator dynamics. And okay, so this, I don't know whether I say that elsewhere, but there are quite a few talks on this, so that probably will get mentioned somewhere. So this in general need not converge, but there are some special cases where, so if UI is some gradient of some function, so for UI x del by del xi of fx, that's called a potential game, then you can prove convergence. And yeah, that's probably the most important case that I know. In general, I mean, the biologists are interested in something else. So suppose this is my probability simplex. They're interested in because it's UI is multiplied by xi, any face of the simplex is an invariant set. But when it is inside, it can approach the invariant set only asymptotically, because if it hits that, I mean, that cannot happen because this is an invariant set, it would have already been there. So they're worried about something called persistent, which means you shouldn't, I mean, no species should die. So this UI typically corresponds to the payoff to species I given the whatever the payoff profile X. And then what it says is that this says is that the species whose payoff is bigger than the population average will be. Have I made a mistake here? Let's see if I think I may have. Yeah, it's okay. I think this will just sum to 1. Yeah, so if the average is above the population average after you plug that in, then that population will tend to increase, and otherwise, what? Hmm? Here.
Yeah. And then xj after summation.
I have, this shouldn't have been there, I think.
No, that would have been common on standard replica.
Yeah, so I have defined Fi as XIUI. Yeah. But still, I think there's one xi too many somewhere. Or maybe it is not a special case of this for all. Yeah, I think this, I should not put it as a special case of this. The next one is a special case of this. This is no, not here, next slide. Anyway, let me complete what I had to say about this. So it is also, so just as you saw the somewhat similar to the earn model, if I do this, okay, so here I'm sort of, I have some weights xi assigned to some n option alternatives. I update the multiplicative, some performance measure fi of the collective performance measure, but for different for each I. Xn is the entire vector. I want to update xi by multiplying this. That's why it's called a multiplicative weight. But I want it to remain a probability vector, so I normalize it again. So it's called a multiplicative weight algorithm. It's quite effective. And there's a paper by a long sort of survey article by Arora, Hazan, and Kali, which talks about this. And Sanjeev Arora actually believes that this should be taught right in the beginning in computer science courses. So if you take a, again, more or less clear that if you go to a continuous time limit of this, it again gives you replicator dynamics. Yeah, okay, I've said all this. Yes, this is a replica. Okay, there's one way of using, one way to prove, analyze asymptotic behavior is to take V as a Lyapunov function. Also, another way is to change variable to positive square root of xi. It makes it a gradient descent on the positive orthant of unit sphere. Now, if you take fi as this, then this is yet another dynamics. And okay, these have been extensively studied, and there are books about it. So, and probably several lectures here will address this issue. And yet another thing from game theory, this fictitious play, which is already mentioned. So again, I have a d-dimensional probability vector. Xi is the probability of agent I choosing 1. I'm assuming only two actions, 1 and 0. And x minus I is the d minus 1 dimensional vector of the rest of the crowd. So I just drop the ith component. And fi x minus I is the best response for mixed strategy of I when the strategy profile of other agents is minus xi. So fi of x minus I is the probability distribution on the strategy set. So assuming that this is unique, which need not be, I mean, these things can get quite complicated. I'm taking the very vanilla case. So if xn is the fraction of time still n agent k played 1, which is, suppose you take that as agent k is mixed strategy. Suppose I believe that that's the mixed strategy of agent k, then you get this OD limit. Now, if there are just two agents, then somewhere in Michel Benham's work, he has analyzed this. So suppose this is a nice function, fi is continuously differential, etc. Then you see that the divergence of the right hand side is negative. It's minus 1 or minus d. Sorry. So the volume shrinks. So if it's in 2 dimensions, it's asymptotically one dimensional, and any bounded one-dimensional ODE. Actually, I should have mentioned this when I talked about earn model also. Any bounded one-dimensional ODE has to converge. It has nowhere to go. So if you have a straight line, you have some ODE going somewhere. So if it's bounded, so if it keeps increasing, it has to converge. If decreasing, it has to converge, and it cannot turn around because at any given point, the direction is specified. So scalar ODEs, well-posed scalar ODEs have to converge. So this will tell you that asymptotically it's one-dimensional. This is not a proof, just an intuition. So he does that for prisoner's dilemma. So generally it gets messy, and this is something else picked up from some other source. That this also somewhat misleading, because if I consider these two, suppose the payoff is 1 if both say both draw 1 or both draw 0 and 0 otherwise, then the empirical frequency of these two pairs are identical, but payoff is always 1 for this and always 0 for this. So this kind of issues, I can give you the source also. It's discussed in a book called Strategic Learning and Its Limitations by H. Peyton Young. And there are several other dynamics. So this is a nice survey. And actually, this book by Sigmund and Hofbauer has a sort of enormous amount of analysis of replicator dynamics, including this persistence, etc. Now, this is a somewhat exotic example. Take fi xi ui xi raised to alpha. Okay. And the del pi x by del xj is positive. Oh, sorry, I also forgot to mention that this is differentiable and monotone decreasing. Then what happens is that, so suppose I take del by del x j not equal to I of this doesn't matter, and this is coming into denominator, which is decreasing, so this thing increases. So cross derivatives are positive. So this makes it what's called a monotone dynamics, which I am going to treat again in greater detail. And what's known is that if the trajectories remain bounded, then, which of course this is a Kolmogorov equation, so it's in a probability simplex, so it's always bounded. So then for all initial conditions belonging to an open dense set, it will converge. And also as alpha tends to infinity, this the set to which it converges to amounts to the maximizers of uj. And it's called a Waldrop equilibrium. And this is actually this strange condition, utility decreasing with input, is true in congestion games. So if you are a transportation network, you find a road which is empty, everybody goes there, it's no longer empty. It's congested. And it's used, this kind of things are analyzed extensively in transportation and communication networks. And this Mr. Waldrop was a civil engineer. He gave a verbal description in some article on transportation, where he says that, yeah, basically the traffic will tend to concentrate on routes which maximize the throughput or something to that effect. And the kind of intuition is kind of a continuum of players, and it's a one against the crowd. So for an individual, it's a game, but against the entire traffic. This is another somewhat similar thing. So I consider interacting Markov chains, and with mean field interaction, in the sense that the transition of probability of going from xin to j depends on xin, of course, plus everybody else, but that effect of everybody else is averaged. Now we take the n tending to infinity limit. Suppose so the capital N is the particle size, small n is the time index. So let n tend to infinity limit, it becomes this converges to the expectation with respect to pi sub n, where pi sub n is this limit. Let me use that as a definition. One can show that it works. So pi n actually satisfies, you can show, so this is how you can prove it also. Pi n satisfies this recursive equation. This is a nonlinear Kolmogorov equation, discrete one. Okay. So I'm working with discrete time, so it's a discrete nonlinear Kolmogorov equation, because usually if you consider the probability distribution, suppose pi n is the probability distribution of a Markov chain, that pi n plus 1 I sum over j of pi n j, p I given j. Now there's this extra L and averaging over L that makes it nonlinear. It's a quadratic term. So, and because this is a deterministic equation, if the initial distribution is deterministic, then the distribution will remain deterministic. And or rather that average, sorry, that's not a correct statement. Using that, one can show that this limit exists as a deterministic limit. It depends on the initial distribution. It's not a, I'm making a somewhat imprecise statement, but for example, this is the case often of interest. The initial distributions of the chains are independent but identical. I didn't mention that, the IID. Then in the end, tending to infinity, the chains become independent. And this is a fancy name, propagation of chaos. So the independence is preserved. And the reason is that they're coupled through pi n. And in the limit, pi n becomes deterministic. So they're independent because the coupling is purely deterministic. So this actually, the continuous version will look like this, where P of x is this function here. And this is a sort of, just because I was talking about Markov chains, I have reduced it to Markov chains, but this was studied for interacting diffusions, and it's called a Makin-Vlasov, oops, spelling mistake. There's no K, Makin-Vlasov equation. And this has been extensively studied. And it's also a lot of work on this, probably many of you know, work on mean field control based on this. Mean field control and mean field games also, which is somewhat similar to the Wardrop equilibrium. You have each agent playing against the entire crowd. Okay, so the second class I want to talk about is the well-known stochastic gradient descent. Here, f itself serves as a Lyapunov function because d by dt of fxt is minus norm grad f x t square, which is positive except at equilibria, and the local minima are the stable equilibria, so it will go to a local minimum. Now, this is popular in this empirical risk minimization in machine learning. So for the simplest case, you take some regression problem. I have this data, say IID input-output pairs xn comma yn, and I want to fit a parameterized map f theta. So I want to find theta star which minimizes this expected risk. So you approximate the empirical risk by, the expected risk by this empirical risk. Now there's a catch here, it's not free. If for fixed theta, this will converge to this by strong law of large numbers, but you are minimizing over theta, so you need the convergence to be uniform. So if sequence of functions converges to another function, the minimizers need not converge to minimizers unless the convergence is uniform. So you need something called uniform law of large numbers. So there's in statistical learning theory a lot of work on that. First one, the most famous one is something called one due to Wapnick and Cheroninckis. So this is all over ML, this particular scheme. So the backpropagation algorithm is basically gradient descent, except that you have a multi-layer network, so you split the gradient computation cleverly using the using chain rule and multi-layer structure. A lot of work on approximate gradient. Then if the gradient is approximate and its approximation is good enough, it will converge to a small neighborhood of a local minimum. That's because the gradient, the Lyapunov function will continue to descend till it gets close enough. That's the intuition. So generally that's good enough. So because of which there is a lot of interesting estimation schemes. So there's one famous one called SPSA due to James Paul, simultaneous perturbation stochastic approximation. So there's a 2-sample version and 1-sample version. Basically 2-sample version takes the basically finite difference, but in a random direction, and that's good enough. And the single sample version does something similar, but that has some issues. So it basically, if you consider x plus say delta and write plus higher order terms, then there's two sample version will take this minus this and divide by delta, and of course it's noisy, so I should put noise everywhere. There's a single sample version which does this something similar, but it has it has a small divisor problem. You're dividing by a small delta, so it's numerical issues. Then there's another very clever thing by Mukherjee, Wu, and Zhao. The only problem is that it needs a lot of samples because so if you can sort of evaluate the function evaluations are cheap, then you can use this. But I like the scheme. So it's basically, if you want something at x, so this is approximately true. So suppose I have take multiple samples in the neighborhood of x and do this, say, sorry, minus square, and replace this by y, and treat this as a regression problem and solve for y. That gives a very good estimate. Of course, the problem is that you need to evaluate a lot of xi's. So depending on when it is possible and cheap, it's a very nice scheme. And then there are other things like momentum methods. So add another second order term, which kind of, I have some pictures for that, so I'll explain later. And subgradient descent, which is if you don't have differentiability, use something called subgradient, which is an object. Anyway, I have a picture later. So this is to show the advantage of momentum method. So momentum method just is xn plus 1 is xn minus n grad f xn minus or plus bn xn times xn minus 1. No, I think it's minus again. So the thing is that it's like adding momentum. So if it's a kind of bad landscape, which is pinched in the sense that it's very narrow in one direction and the gradients across are high, but gradients along are slow, it will zigzag, which makes the algorithm gradient descent very bad. So if you put a momentum term, it kind of smoothens out. So this is the intuitive explanation. It also, momentum kicks you out of small local minima. It also calls you to wiggle, causes you to wiggle when you reach the destination. That's the problem, but this helps. So this is a kind of a provably optimal kind of version due to Nesterov. That's more complicated. This is subgradient. So if this is not differentiable, there's some cone like this. You take some direction here and you will still descend. Subgradient descent. The convergence rate degrades though. So this is the third category I had, fixed point seekers. So this hx is fx minus x. I want to find fixed point of some function f. So of course, Kolmogorov the nonlinear Kolmogorov was a special case of this. I feel it's important enough that it should be isolated. This is useful in reinforcement learning a lot. I have not seen too many other examples. So hx is fx minus x. So the ODE is x dot equal to fx minus x. And suppose I assume that it's a contraction with some norm. And that means this inequality holds with alpha, positive alpha strictly less than 1. Then this is a unique fixed point x star, and xt will converge to x star, the ODE converges. In fact, this serves as a Lyapunov function. In fact, you can use this Lyapunov function for the max norm also, although it's not differentiable. Through a limiting argument, you can show that the max norm will decrease if it's infinite norm contraction. And this is useful in reinforcement learning again, because that deals with dynamic programming where you have infinity norm contractions. If it's alpha equal to 1, this doesn't work. It's called non-expansive, and it may have no fixed points. The x to x plus 1 is a map with no fixed points. X to minus x has a unique fixed point. X to x has every point is a fixed point. So you can say nothing in general. But you can show that this Lyapunov function is non-decreasing, and decreasing if the unit ball is strictly convex for any fixed point x star. So let me draw a picture here. So suppose this is x star and I take some ball around it. Doesn't have to be L2, but not infinity. Infinity ball is not strictly convex like this. And also L1 I have excluded anyway, but L1 ball is also not. So P strictly between 1 and infinity. Then we're looking at an ODE, so that's where incrementality helps here. So suppose I was just doing the iteration xn plus 1 is fxn, and it is only non-expansive. I start here, next point could have been here. So I have not got any closer to that. But this is an incremental algorithm, so I just move a small amount. Because strictly convex, I am already inside. So it does work, but here, of course, it doesn't. So that's a hard way to, more difficult to prove things there. But this is the one more useful for reinforcement learning. And there are some cases where other proofs work. So this is, I don't know too many. I have seen one, but there are probably others. See, if you have a nonlinear Kolmogorov equation, it's a probability distribution which is evolving. Okay, probability vector. So a natural guess would be for Lyapunov function would be to the Kullback-Leibler divergence with respect to the stationary distribution. And this sometimes works. For example, for Boltzmann equation, you have the entropy as a Lyapunov function, but that, of course, that's not relative entropy. Here, it's a kind of, I'm assuming some Markov chain. Typically, in Markov chain related things, you look. In fact, if you consider a Markov chain, finite state Markov chain with a unique stationary distribution pi star, then this is a Lyapunov function. The distribution pi n of the Markov chain at time n. D of pi n pi star monotonically decreases to 0. Stochastic ascent descent, this is if you have a saddle point, and you need strict convexity concavity here, otherwise it doesn't work. You use the stochastic. So convex is the one you are minimizing, concave is the one you are maximizing. This works. And the reason is that this works as a Lyapunov function. Now, this works only for gradient systems. I mean, there are other algorithms for saddle points which do not necessarily use gradients, but then one may have to separate the timescales of the iterations, which is something I'm going to do later. Oh, okay, these two are interesting exotica. These don't fit anything, I know, but they're fantastic results. So they have generic convergence. Okay, generic in two different senses. If you want to say generic in topological sense, that means for almost all initial conditions outside, this is a major theoretic sense, outside a set of zero Lebesgue measure. That's a major theoretic generic. This is topological outside a dense open set. So this is Newton flow. This is sort of a continuous time Newton scheme. This was proved by Smale that it generically converges. So if we are doing optimization, so this is for solving the Newton scheme for solving Hx equal to 0. If you are doing optimization, your H is grad f. So you do grad f(x) equal to 0, and this is the Newton algorithm. So this is a pictorial. I mean, the proof is not trivial. I'm just going to give some basic idea. What it proves is that using calculus basically is there's something I have to assume that okay. Suppose these are the set of equilibria, and I can enclose them in some region with nice boundaries so that all arrows point inwards. Then if I start at somewhere, it proves that grad f(x) by this norm, assuming this is not 0, remains constant along this trajectory. That's pure calculus. I mean, it's not trivial amount of calculus, but calculus. And then what can this trajectory do? It cannot arbitrarily, I don't know if I say that in words. So it cannot come arbitrarily close to it. So it's well posed, so it cannot come arbitrarily close to itself, because well posedness says that if this is my trajectory, at some point, there's some neighborhood in which it's the only trajectory solution. So it cannot keep coming. I mean, two dimensional can't even draw it, but can't keep coming arbitrarily close to it itself. It cannot just end somewhere like that, because again, this is constant. Implicit function tells theorem. Oh, sorry, this is from implicit function theorem. You knows that this is what is okay. Let me backtrack a bit. Grad f x is a d-dimensional object. This is norm grad f x is a one-dimensional object. So this is a map from RD to d-dimensional sphere, which is d minus one dimensional. Okay. So whenever this is kind of allows the use of implicit function theorem, this will be a one-dimensional curve. So when it shows that this is constant, this actually is equivalent description of the curve. This curve is defined by grad f xt by norm grad f xt equal to constant. The constant may depend on where you start. But given that implicit function theorem tells you that at any point in a neighborhood, there will be no other, it will be the only sort of manifold corresponding to that. And therefore, it cannot come arbitrarily close to itself. It cannot just end somewhere like this, because again, at this point, implicit function theorem allows you to continue the solution for a while. So it cannot come or fold onto itself, cannot stop somewhere, it cannot go out because the arrows are pointing inside, inwards everywhere. So it has to converge. So this for almost all initial conditions, because to justify all this, he uses, to justify the use of implicit function theorem, he uses the something called Sart's theorem on this surface, which allows this to happen only almost everywhere with respect to the surface measure. So that's a technicality, but amazingly clever idea. And it's also amazingly little known, because he was trying to prove that I think I have here. He went through various, he kind of changes interest every now and then. So he went through a phase he wanted to do economics. So yeah, this is what you are trying to justify this process, that some convergence to economic equilibrium by incremental learning by adjustments by economic agents. So he proved this, and then he published that in Journal of Mathematical Economics, which mathematicians don't read, or optimization people don't read either. So it's undeservedly unknown in this, definitely in optimization community, because I know about other mathematicians I don't know. So in optimization, this is okay. The one this is just for intuition for that Hessian inverse in front kind of. So I said that the stochastic gradient descent is miserable because in pinched landscape where some directions are pinched and others are decreasing slowly, and by putting Hessian inverse in front, it kind of rescales the landscape, and that's why Newton schemes work better. Except that the inverse is hard to compute, so there are these quasi-Newton schemes which recursively compute the. So the Sherman-Morrison-Woodbury formula allows you to recompute inverse of a matrix given inverse of another matrix plus a low rank correction. So these are our practical schemes. Okay, so this is what I mentioned, the cooperative dynamics by Hirsch. So if the irreducible in the sense this is Jacobian, if the cross derivatives are non-negative and the positive ones should form an irreducible matrix, if I remember, then this leads to monotone dynamics in the sense that if x prime 0 is, if the initial conditions is a partial ordered thing, so they don't have to be true. It's a d-dimensional space, but if initial conditions satisfy the domination relation, that is retained in time. And if the trajectory is converged to a bounded set, they converge for almost all initial conditions. Here it is for open dense set. Any questions about it? This is, sorry, I already used it once, but useful fact. Again, for proving convergence algorithms and so on. Any questions about this? Or? Anyway, I'm just going through a long laundry list of facts and factoids. In case there are any questions, don't hesitate to ask. Not that I will be able to answer everything, but I can try. Okay, some extensions. So this is the distributed asynchronous schemes. It writes this. It definitely will happen in multi-agent learning algorithms, but it also happens because sometimes spread your computation across multiple processors. That was the original motivation for studying this kind of thing. So this yn, see, the assumption is that I am not updating all components at the same time. So yn is some random subset of the index set. So suppose I goes, so suppose I, in fact, each of these can be a vector iteration, and I denotes the processor, ith processor. So, okay, let me stick to components. So suppose this is the ith component, and yn is the set of components which performed an update at time n. So if this indicator is 1, xin plus 1 is xin plus this, all this. If this is 0, then xin plus 1 is xin. No data was made. Then these are delays. It's assumed that you get information from other processes with or other agents with some delay. And new in is the local clock. It's the number of times ith component was updated till time n. Now, this has one advantage. See, I can also put these algorithms have also been analyzed with just an there. But a new in has an advantage. It has a nicer theory to start with under extra assumptions. But if the processor I needs to know only new in, namely how many computations the processor did, then it doesn't have to know n. N can be some sort of abstraction in the background. Tau jin are delays encountered by I. Now my claim is that if this remains bounded away from 0, that means this is the frequency with which I was updated till time n, the fraction of times I was updated till time n. So it should remain bounded away from 0. That means you are updating everyone comparably often. Then one can show that convergence results apply. I don't know if okay, let me just explain why. One thing is that because n is going to 0, the time scale is being squeezed. So if I assume that these delays satisfy some reasonable moment condition, they get squeezed out. They will slow down the convergence and worsen the errors, but asymptotics doesn't change because of the delays. Delays are not a problem in the for asymptotic convergence. They will just get squeezed out. Okay, so suppose that deterministic delay of capital T, it will get translated into a of whatever sum of am from some t to t plus capital T. That will be sorry, that was wrong. It will go from plus say sin, where this is such that this is the first time. I don't have to remember this just. Something like this. Anyway, it doesn't matter. The idea is that I have this, oh, maybe I do have a picture. I don't remember. No. So suppose my step size is 1 by n plus 1, then sum of n goes like this. And suppose I consider intervals of width t here, and keep moving it to the right. Then this will get mapped into something smaller. As it moves to the right, it gets mapped into something even smaller. So the error it contributes goes to 0. But the asynchronous part, the yn is a problem. And what happens if we use new in instead of n? It kind of balances out the time scales asymptotically under extra conditions. It should not always. And that's because if I consider, say, this is the time scale of actual time scale relative to synchronous time scale. It's roughly this, and this term remains because this is bounded away from 0. This remains bounded, so they asymptotically match. So time axis is kind of shared by all components evenly. Of course, it will slow down the algorithm, but this requires that this thing grows like log or slower than log. So not all choices of n are legitimate here. So 1 by n raised to 2 by 3 won't work. So more generally, you get some, if you don't worry about anything, you get some junk sitting in front. There's some diagonal matrix with non-negative terms on the diagonal, which represent the relative frequencies with which various things are being sampled, various components. And if they're bounded away from zero for gradient descent and fixed point algorithms in reinforcement learning, it doesn't matter at all, because see, I said that this value, the function v, sorry, f itself is a Lyapunov function, because d by dt is minus sum over I minus, sorry, might as well read this grad f. And here what you get is this gets replaced by minus sum over I lambda I t times the same del by del xi, which is still negative away from the equilibrium. And something similar for infinite norm contractions. You get something time dependent, it's still a contraction with a common fixed point. It's easy to check. Okay, maybe it's a good point to stop. This is a kind of longish affair. Any questions? Yeah. Anyway, this stochastic gradient descent is used extensively. Yeah, so it's used for training neural networks and many other things, but this fixed point iterations will come in reinforcement learning, in the dynamic Markov decision process. And first, yeah, the nonlinear Kolmogorov has been used for various. That is the last one actually, which I mentioned, congestion control actually, and some colleagues use for some communication network kind of. Earn models, of course, have been extensively studied. You heard of elephant random walk? This there also some people are trying to use this. An elephant has infinite memory, so it with some probability. So at time n, it picks some time point from 0 to n with some probability and repeats that step with probability p, and with 1 minus p takes makes a fresh decision, pure random walk. So random walk with increasing memory. Large fraction of ISI probabilities after elephant random walk. No, zero-sum games generally is an exception where many things work. So they are not expected to converge, is it? The no. Stochastic gradient descent, I'm not familiar. You are saying it converges? No, I'm asking because in the zero-sum case, one player is optimizing equation F, and the other player is like, oh, then it will reduce to the saddle point, not the gradient descent. Yeah. I have that saddle point equation. If they are concave or convex, then it will work. But in the reinforcement learning for Markov decision process, so you go to zero-sum game, doesn't change much. You just replace min by min max. I mean, at least mathematically, it doesn't change much. But anything other than that becomes very hard. Okay, so we will continue. Yeah, sorry.
So, in the context of the Newton flow, you mentioned that by pre-multiplying the inverse of the Hessian, so it balances the landscape to make the convergence potentially well behaved. So, can the similar idea be applied in other contexts like replicator and others as well? Or is it only specific to optimization type of software?
I don't know whether it has been applied to replicator kind of things, but there are, I mean, somewhere, maybe if I go to RL, there are some algorithms I mentioned where something which is reminiscent of Newton's scheme appears. The LSPE algorithm, do you know, least squares policy evaluation, that has some matrix in front of what you would otherwise have. And so this ZAP Q learning, have you heard of it? Sean, he also does something similar. There's a lot of coupled iterations. One of them, there's some Newton-like object in front. That speeds up. Of course, it increases the computation, but it's much faster.